All right, everyone, welcome. Take a time. I'm just going to go through. So we got a couple of presentations. I had Peter up first.
Yep.
Okay, so let me stop sharing so you can share your screen.
Share my screen.
I think I just, there's David. Bounced around there. You'll be up next.
Can you see my screen?
Yeah, and I see myself, which is
No.
disturbing.
All right, let's get this. Hopefully I can run this and all, right? Or is it preview? Oh,
There you go.
Okay. All right, so our presentation on chapter 5, question 9. So here's our problem statement. So in 2013, the Pew Research Foundation reported that 45% of US adults report that they live with one or more chronic conditions. And the standard error for this estimate is 1.2%. So we're given a bunch of statements and we're basically going to identify if they're true or false. And we have to provide an explanation to justify each of our answers. So part A, the statement was, we can say with certainty that the confidence interval from exercise 5.7 containing the true percentage of US adults who suffer from a chronic illness. So for reference, question 5.7 basically asks us to construct a 95% confidence interval for the proportion of US adults who live with one or more chronic conditions. So the confidence interval is based around a Pew Research Foundation study that randomly sampled US adults across the United States. And basically the statement is false because this is a 95% confidence interval, but it's not 100%. So there's a 5% chance that actually does not contain the true percentage of US adults that suffer from a chronic illness. So this statement in part A is false. For part B, the statement is, if you repeated this study 1,000 times and constructed a 95% confidence interval for each study, then approximately 950% of those confidence intervals would contain the true fraction of US adults who suffer from chronic illnesses. So this statement is true. By constructing a 95% confidence interval, by constructing 1,000, sorry about that, I didn't write that down. By constructing like 1,000 95% confidence intervals, 95% of those confidence intervals generated from randomly sampling the population will contain the true fraction of US adults who suffer from chronic illnesses. So this statement is true. And for part C, the statement says, the poll provides statistically significant evidence at alpha equals 0.05 level that the percentage of US adults who suffer from chronic illnesses is below 50%. So in order to do this, we actually have to determine the confidence interval at a 95%. So that's what I did here. And if we look right here, it is 0.45 plus minus 0.024. So the upper bound of this confidence interval is still below 0.5. So this statement is true right here. And part D, the statement is, since the standard error is 1.2, only 1.2 of the people in this study communicated uncertainty about their answer. So this statement is false because the standard error is a measure of the uncertainty of the overall estimate, not of like the individual people. And that was the last part of this question.
Great.
So yeah.
Thanks very much, Peter.
Mm-hmm.
All right, David, you ready? Oh, there we go.
So I selected question 5.13. And the overall question was around website registrations. And a website is trying to increase its registration of first-time visitors, exposing 1% of these visitors to a new site design of 752 random sample visitors over the month who saw the new design. 64 registered. And so it asks 3 different questions. And so the first question is, check any conditions required for constructing a confidence interval. And so the first condition is independence. So sampled observations must be independent. So random sampling assignment is used. And then if the sample is without replacement, then N must be less than 10%. And then the other piece was sample size. So ensuring that N multiplied by P is greater than or equal to 10. And N multiplied by 1 minus P is greater than or equal to 10. So you can either look at the N and the X to define that, or you can actually work the calculations out, but both of those items are true. And then the next question is compute the standard error, and basically it's using X, N, and P hat to calculate the standard error, which is P multiplied by 1 minus P over N, all square rooted. And the number for that is 0.0102. And then the question C is create a 90% confidence interval, construct a 90% confidence interval for the equation. Did some of the calculations around defining what the Z value should be. And then basically the confidence interval ends up being P hat plus or minus the Z value multiplied by the standard error. And calculating that out, we end up with 0.0683 and 0.1019.
Great, thanks so much. All right, let me get my screen back. All right, bring up the chat. All right, so tonight we're going to basically extend. So this week and next week, if you feel pretty good about the central limit theorem, we're just going to make some minor tweaks and kind of leverage that and talk specifically about making inferences with tonight categorical data and then next week numerical data, even though kind of looked at them a little bit next week. We're expanding where we have small sample sizes, bigger groups, and then tonight we're kind of looking at proportions and different groups. But the process is going to be very much parallel, and so you basically over these 4 weeks or so, getting, I think, coming out of this section and after next week, having a really good understanding of what like null hypothesis testing is and how it works and why it works. I was thinking about this over the last week because one question that may come up, no one actually asked it, but it might be pertinent for data scientists, is like oftentimes, you want to get to prediction, and we're working our way there, but this kind of stuff is going to show up over and over again, because even when we get to predictive modeling, we're often going to look at the whether or not particular predictors are significant in predicting some outcome of interest, and the way we do that is through various null hypothesis tests. So I think it's kind of important to kind of really have a good grasp of what's going on here. And also the distribution stuff, as we start to expand, and we'll see a new distribution tonight, in fact. But if we kind of have a good sense of the normal distribution, hopefully it makes it a little bit easier when we get to some of these other ones. So we're going to start with sort of a question that's from the general survey, GSS, General Study Survey. I can't remember what it stands for now. I'm drawing a blank, but I like this question. As a quick review from like chapter 1, we have this question that was posed to people who are, we have these 2 scenarios for testing the effectiveness of a blood pressure drug, right? And we have one scientist who wants to give the drug to 1,000 people with high blood pressure and see how many of them experience lower blood pressure. And we have some other scientists says, well, what if we give it to 500 and not give it to 500 and look at the difference? So the question right here is, which is the better way to test this drug, right? And of course, everyone knows the answer is 500 get and 500 don't, because we had a lengthy discussion about causal inference, right? And we want to be able to control that and look at that difference. But this question was posed, so we're going to look at this as if it's a survey response. And so in 2010, this was asked to a bunch of people, 670 people. And these are the counts that we got from the survey, right? Pretty common. We do a lot of surveys, we get a response, and we want to know something about the proportions, and we want to say something about the population. So presuming this is a random sample of all Americans, right? We want to say, well, what's the proportion of Americans, right, that have good intuition on, a causal inference or a randomized control trial. So it's 571 out of 670. So, right, nothing terribly new here, except we're talking about proportions now instead of means, right? And we can think of the proportion as a mean, in terms of these kind of data. So this is what we're interested in. Of course, we're gonna do this based upon a particular sample, which is the p hat. That's our observed sample. And so we can approach this using the same confidence interval approach, where we have some point estimate plus or minus some margin of error, right? And remember, last week we really were talking about, we called it the standard error when we were talking about the mean. When we talk about proportions, we're talking about margin of error. We're just going to use a slightly different phrase, but it's still the standard deviation of the sampling distribution. Just in this case, the sampling distribution is of proportions. And because we have proportions, we need to calculate it a little bit differently. So when we talk about standard deviations, we're often, we're looking at sort of a variance estimate. So you probably would expect to have a square root and some kind of multiplication going in. So the standard error, I'm not going to go into the, derive this, but the formula is we have the probability of success, right? Quote unquote success. I'm going to use the term success and failure here, but it really just translates to group A, group B, right? Is another way to think about it. So it's proportion of success times the probability of success times the probability of failure over n. You take the square root of that whole thing, right? And so the central limit holds for proportions here. So as n increases, as our sample size increases, that sampling distribution is going to approximate the normal distribution, where the mean is equal to that proportion of success, whichever group you're going to have, and the standard error is equal to this equation here, which is the margin of error. We do have a couple of assumptions here. We have an independent assumptions. So what we mean by that is that each observation is independent of each other observation. And this is, this can be pretty important. And then we have to have at least 10 successes and 10 failures. And so if we go back to that survey, right? So we had 571 out of 670, or 85% of those surveyed got the experimental question correct. Right. And so we want to get a 95% confidence interval, like where we want to say with 95% certainty that we probably captured the true population mean. Right. So here are our givens. We get a check condition. So it's a random sample. Okay. So that's key. So, and we're making an assumption that the response to one survey respondent isn't influencing another. And we also have this other kind of condition here that 670 is less than 10% of all Americans. And I actually got a couple of slides, a little simulation to explain why we have this particular condition, right? So we want big sample sizes, but as the sample sizes get bigger, this could be a problem. And we'll just hold on to that for a moment. I'll show why. And then we have the success, right? We need at least 10 successes and 10 failures. You can think of this as the minimum sample size. So last couple of weeks, we said our sample size should be at least 30 for the normal distribution to kind of, for that sample n to be large enough for the central limit theorem to hold. Okay, and so they're both greater than 10. So here we can construct this. So we're going to use 1.96 times our standard error. We get a confidence interval. So what we could say is we're 95% confident that the true population proportion of Americans that have good experimental intuition or knowledge is somewhere between 82 and 88%. Okay, so nothing terribly new. We're just now applying it to proportions. Oh, I'm sorry. There's a question. Is there a question? Oh, no, sorry. All right. Here's another question. Like, as we enter, as this is probably a little less, it not being a major election year, but sometimes in the fall, like next fall, we'll certainly see a lot of polling, and if you start to see polls in whatever news outlet you see, take note of the sample size as you go. You're going to see that they're all going to be somewhere usually between 1,000 and 1,100. And so question is like, why is that? So let's consider a situation where you want to conduct a survey, but you want to have a 3% margin of error. You want your margin of error to be small enough that you can say something with certain meaning. Then how many people do I need to sample to get a 3% margin of error? So to do this, we can start with the assumption of that the proportion's 50-50. The reason why we're doing that is that's going to be the worst case scenario, because that's going to make the numerator the largest. It's just going to make this product here largest. So if we assume 50-50, if we end up with something other than 50-50, well, this ratio will obviously shift and will shrink the standard error. But if we're at 50-50, that's kind of the most conservative estimate. And so we can just solve this out, and N is approximately 1,068. And this is actually pretty common. So you'll see this roughly this number used by pollsters. And what's kind of interesting is that the increase in N here is not linear. In order to get to like a 1.5 to kind of have the margin of error, you need to increase N, I think, by roughly an order of magnitude. You can do the arithmetic later. So it's kind of curious, like why P equals 0.05 sort of convention, 3% margin of error seems to be like getting 1,000 random samples is enough to, for the effort. So that's kind of where that comes from. And that's where pollsters get that from. So let's look at an example with two proportions. So we're looking at the general, the GSS survey. Then here we have some responses from Duke students. Just as an aside, why Duke? Well, the authors of the textbook were teaching at Duke at the time they wrote the initial book. So one of these semesters, I want to do it with CUNY students. So, actually, we're going to shift the question. I'm sorry. We're going to now look at whether or not we think global warming has big effects on the polar regions in the next 100 years. And so we have a great deal, some, a little, not at all. So we got 680 from sampled from all Americans, and then 105 from Duke. And what we're actually going to do here is dichotomize this. So we're just going to look at a great deal and everything else to look at two proportions. But our parameter of interest is a little bit different here, right? Our parameter of interest is actually the proportion of Duke minus the proportion of US, right? And so we're going to use our estimates to get there. So again, nothing a whole lot different. We're still using the hypothesis test, right? Where we have some point estimate that we're going to calculate minus some null value. In this case, our null value is going to be 0, but it doesn't have to be 0. But it is often 0. So that part gets kind of removed. And our standard error is just slightly different because we have two proportions. So we need to account for both. So we have proportion of group 1 of success times failure over N, and we're going to add in the other group there as such. And that's going to give us the standard error for the difference of two proportions. Now we got a couple of, we got two of the same. Well, we have an independence and success failure. So success failure is we need to have at least 10. Success is 10 failures. Not anything different there. But the independence has to be stated a little bit differently because we're talking about independence within groups and between groups. And so within groups, I think we're pretty good, right? Because we randomly selected all Americans and we randomly selected Duke students. And the number of Duke students we had is less than 10% of Duke students. Got to be careful here, right? And the 680 is less than 10% of all Americans, of course. We also need independence between groups. And this one's a little bit actually admittedly problematic here. And again, I have I think a couple slides that show, what happens as this ratio shifts, right? Because Duke students, some of them, maybe a lot of them, I actually don't know what proportion, are also Americans, right? So they could reasonably be, be included in the American sample, right? So there's a little bit of a violation, but the ratio is so small, right? Duke students, is a fraction of a percent of all Americans, that the likelihood of that happening is very small. And if it happened, with one student, that wouldn't be that big of a deal. But this is something you should pay very close attention. Ooh, boy, I went all the way to the end. Because that, shoot, where am I? I'm so sorry. Okay, but yeah, I'm just mentioning this as something to be careful. Like a situation where you have one group that's a subset of another group. We do this quite a lot, and I'll give some guidance at the end as to how big that subgroup needs to be before you really need to worry about it. But we'll just say our conditions are met. And so we got a great deal, not a great deal. And so, we have 65.7% for Duke and 66.8. We're using 1.96. We're using a 95% confidence interval. We calculate this all out. We end up with a confidence interval between negative 0.1 and positive 0.086. And since this confidence interval spans 0, meaning 0 is a possible outcome, we would not reject the null hypothesis under this scheme. So there is no difference between, we would say there's, the data doesn't support there's a difference between the proportion of Duke and US and Americans' perception on global warming, given this question. Let's look at another one where we have actually a whole lot of groups. I find this a super interesting example. So Weldon in the late 1800s was a biologist who in 1894, I find this unbelievable, but he did it, rolled 12 dice 26,306 times and recorded the numbers of fives or sixes, which he considered to be a success, right? He observed that 5s and 6 occurred more often than would be expected. And then later, Pearson, who we'll see his name quite a lot coming up, particularly when we talk about correlations, because he kind of invented that, hypothesized that this probability was due to the construction of dice and more, inexpensive dice. They hollowed out the pips. And since the opposite sides add to 7, right, the ones, a couple sides were a little bit heavier than the opposite sides. So that was Pearson's hypothesis. So in 2009, Labby at the University of Chicago created a device to recreate Weldon's experiment. And if you click on this YouTube, you can actually see the machine. It's about a minute, but let me jump ahead. So he kind of did this whole thing, and some of you may be interested that that he did this in 2009. Somewhere in here, there's even shows how the image processing works to actually do the counting. So, anyways, I find this super interesting. So he replicated that, and what's kind of amazing is his machine. It took about 20 seconds per roll, and so in order to get Weldon's data set or replicate it took him 6 full days for this machine to run. So I don't know if we actually know exactly how long it took Weldon to collect this data, but it must have been an incredible amount of time. So I like this story too, as data scientists, as we are sort of data rich right now and like swimming in data. Think about what people used to do only a century and a half ago to get data. And here's a bar plot with the results, and this horizontal line is the expected value. We would expect, I guess, 1/6 each number to appear 1/6 of the time, and we have some confidence intervals here. There's also a paper here from Labby, and so what we're trying to do here, what's is, so we have this expected value, and it's 50 out of all 315,672 rolls. We would expect 52,612 of each number, right? So I want you to take a moment. So what we're trying to do is saying we have some notion of expectation, and we observe something, and we want to know whether or not what we observed is different than what we expected. And as you get into advanced data science courses, this is going to be used a lot. We're going to have a model where we have some expectation, and then we observe something else, and we want to know, is what we're observing different than our expectation? Is this model, different than some other baseline model? And so we're talking about dice here, but this approach is going to be quite useful as you go forward. So here we have the observed, and they obviously the totals should add up to be the same, right? So so we're setting this up as a null hypothesis test, as we do a lot of things. So the null hypothesis is that there's no inconsistency between observed and expected counts, right? So then the alternative hypothesis is that there is some inconsistency and they don't follow the same distribution, right? So in this case, we would presume there's some bias in the dice, right? So to evaluate them, we're going to quantify how different the observed counts are from the expected counts, and larger deviations from the expected value, or larger variance, right? We'd expect some variance, right? In the same way, when we flipped a coin, if we flipped a coin 100 times, we would not be overly surprised if we got 55 heads and 45 tails, right? That seems to be within reason. But if we got 90 heads and 10 tails, right, clearly we would reject that. And so we've been using normal distribution. But what we need to do now is introduce another distribution, because first of all, this is bounded because we're actually talking about counts. So we can't have anything less than 0. So our test statistics is going to be bounded by 0. But this all fits into something called a goodness of fit, right? We want to say, how good does our data fit an expected distribution, right? And so let's talk about, when we talk about a test statistic, what are we doing, right? We've seen this, but I don't think I've talked about it in a whole lot of detail, right? We have some point estimate. This is what we observe minus some null value, right? And that's often our expectation. And then we have some measure of variability, if you will. In this case, we're talking about the standard error of the point estimate. Okay. And so, this helps us, devise this test statistic. So in the case of this count data, the particular test statistic we're going to use is called a chi-squared, right? And so the chi-squared statistic, what we're doing is for each cell, right, each row here, or each outcome that we have, in this case, we have 6, but we can have as many as you need. We have some observed value minus some expected value, and then we're going to square it. So the squaring is kind of key here because it does a couple of things, because that, first of all, it ensures that all the values in the numerator are positive, right? Because if we have a negative number, it's going to become positive once we square it. And then it also sort of has this built-in penalty for observations that are further away from the expectation. So that can also increase that numerator in ratio to the, in the denominator, we have that actual expected value. And so the further it gets, the further away, the larger that particular contribution. And so K here is just the number of outcomes that we have, or number of cells, if you will. Right. So easier kind of walk this through an example, right? So we have outcome 1. So we have 53,222 is what we observed. We would expect 52,612, right? So we're going to take that difference, square it, and then divide by the expected value. And we get, the value for this iteration of 7.07. We're going to do that all the way through. And we end up, we're just going to sum this last column, which ends up with a chi-squared statistic of 24.73. So this is going to be our sort of measure, our test statistic, and we're going to want to quantify that. So chi-squared, unlike the normal distribution, right? There's the normal distribution, is actually, there's like a class of functions. So we have to introduce this new concept called a degrees of freedom, right? And so the degrees of freedom is directly related to our n. Oh, and as we'll see coming up soon too, can also be related to next week, we can have multiple degrees of freedom in terms of count and cell size. But for chi-squared, we just have to talk about the n. So degrees of freedom for chi-squared is going to be n minus 1. So we have this additional parameter. So there's not a single chi-square. So here I have a plot that shows, here's the blue line. Well, first of all, note all of these distribution lines are bounded at 0, right? And that's because we have that square in the numerator. The chi-squared is always going to be positive, right? So, I know we talked last week a little bit, one-tail, two-tail test. With chi-squared, it's always a one-tail test because we're bounded at 0. So when we get our p-value, we're always looking to the right side of the distribution. So if we have 2 degrees of freedom, right, that's this blue line, right? So you can see, where would we need to be for a critical value to have 5% of the area to the right, be over here, where for, as the degrees of freedom increases, as we go to say this red line where we have 9 degrees of freedom, right? We can go further out to the right. So we would need a larger chi-squared to kind of reject the null hypothesis. So I think I said something wrong. I totally apologize. It's not n minus 1, it's the number of groups. So in this case, k is 6, so our degrees of freedom is 5. I'm so sorry. So I got stuck in my head. We'll see when we talk about the F distribution next week. We have n and k that we have to consider, but it's just k minus 1. So so here we get the p-value, and we have a chi-squared with 5 degrees of freedom. And so the p-value, so if we go way out, in fact, I had to tweak this plot to get to 24, right? So we're looking at here, and we're looking at the area to the right, which is technically shaded, but it's so small you can't even see it. Is less than 0.0001, right? So very, very small p-value. So in this case, we would reject the null hypothesis, right? So the 1,6 axis is consistently shorter. So in case you're wondering or thinking about running to Atlantic City or Las Vegas, you should know that now in casinos, they use high quality. They actually fill the pips, so they are well balanced. So this is no longer the case. So you can't cheat that out. Let me jump over real quick because I have this Shiny app too that you can run. Let me put the R command. It's in the data 606. So once you load the data 606 package, this is very much a work in progress, but you can run this app. So right now I have normal, right? So we're kind of used to that. So here we can see if I have, what am I doing? Standard, this is standard normal because I have a mean of 0, 1, right? We can go through this, but let's look at the chi-squared. So here's a chi-squared with 2 degrees of freedom. And if I have a critical value of 2, right, I'm going to have 0.038. So to get to 0.05, my critical value, at some point I want to tweak this so I can put in the p-value. So but for now, I'm just going to kind of drag this until I get close. That's probably as close as I'm going to get. So a critical value of 6 is roughly 0.05, right? But as I increase the degrees of freedom, right, that critical value can be larger before I would reject. So we had 5 degrees of freedom, right? So, and let me increase the upper plot limits, right? So we can go to, in fact, my app, it'd have to be large, our critical value would have to be larger than 10 to reject the null hypothesis. So as our degrees of freedom increases, right, we're going to need more variability across those groups to actually reject the null hypothesis here. But a couple of points, major things I want you to think about here is really it's as these degrees of freedom change, right, that shape of the distribution is changing. So how we get those p-values is going to change. Questions about this? So we're going to see a couple of distributions like this where we're going to introduce 2 more actually next week, where it's not a single distribution, sort of class of distributions that has some other parameter. So this notion of degrees of freedom that is going to be critical to defining the shape. So the chi-squared does not approximate the normal distribution. And that's because it's bounded. So it really can't, because you never have negative chi-squared values. We're dealing with count data. So there's Poisson is another one where it's sort of bounded. So there's a few like that. So when we're talking about count data and things like that, when we talk about quantitative variables, we'll see things. So, and we'll talk about the t distribution next week. All right. So as a quick recap, right? So, but the notion here, the principles are the same, right? We still have a distribution, the area under the chi-squared from 0 to positive infinity, or if you wish, negative infinity to positive infinity, but it doesn't go below 0. The area under this curve is always 1. Okay, always 1. All right, so this notion of independence between groups, I said I would just briefly talk about this. So this question actually came up a number of semesters ago. So here, why do we need to have independence between groups? So the way to I tried to tackle this is, well, let me stipulate some givens, right? So I'm going to have, have 2 groups, A and B, right? And the probability of success, if you will, for A is 55%. And the probability of success in the group B is 60%, right? Those are given. All right. And all I'm going to do is vary the sampling procedure, right? So the N of A is 99,000, or no, I'm saying 99,000, which is 99% of the population. And group B is 1,000. So to go to our other example, imagine our population for the GSS example, right? We're saying there are let's just say there's 100,000 Americans, 1,000 of which are also Duke students, right? If you want to make that direct parallel to the example we did before. Okay. And so what I want to do is, so there's 2 ways I can randomly sample, right? So I could just randomly sample all Americans. So when I do the American, the group A sample, I can just randomly sample from the 100,000, right? Or I can randomly sample from the 99,000, sort of subtracting out the Duke students, right? And then group B is, I'm always just going to randomly sample from that 1,000. Okay. So far, so good. All right. So I'm going to do that over and over. So you can see I have, and I'm trying to talk through the logic because this is kind of how I try to understand a lot of problems. I build up myself a little simulation. Right, so I'm fixing the proportion of A, 55, proportion for group B is 60, total population is 100,000, sample of A. So from group A, I'm going to sample 1,000 Americans, and sample B, I'm going to sample 100. Okay, or I'm going to start with 100. So I'm going to create this data frame where I have a column called group and a column called response. So I'm doing some sampling. And then I'm just, so we can look at this. Maybe I should, so we can interrogate some of these bits here. Wish that didn't lock me out so quickly. So if I run that, right, and then I can run this. Oops. All right, so if I look at the population data frame, right? So I have group A and I have this response such that I should have about roughly 55 and 65%. Okay, so actually I have it right here, right? So here's what's the mean. Since I coded this as 0 1s, the reason why I did that is, well, if I do that to get I can actually just use the mean function to get the proportion. Right, so this is super handy, convenient way of doing it. So I get 54.1%, which is close to what I wanted. And then the proportion of the population sample, excluding B, is actually 54%, roughly the same. And then for group B sample, I get 70%, which is a little bit higher, but my sample size is smaller. So I would expect a little bit more variability. But what I want to do is now I'm going to loop through this. Actually, I'm going to do lots of random samples. So let's look at these 2 lines. So here, the top line, that's the B, I'm sorry. So A is, which is the, I gotta get this right. Yeah, so B is the smaller group, right? So this is like the Duke students. I'm always just sampling from the Duke students. And so that's pretty stable. But what's key here is as I'm going through, I'm starting at say 0.1 and I'm going up to 50%. So the key here is looking at this green and this red line. So this green line is I am sampling, I'm sampling from Americans, but just all Americans, meaning Duke students are still in there, right? And when I get to a case where, well, actually, I think there's separation at about 10%, right? That was the rule we said, right? And so this red line is I'm sampling from the larger group, but excluding the Duke students. This would be like sampling from Americans, but excluding Duke students. So if I do that, right, then I'm ensuring independence between the two groups. And so that estimate for the population is actually stable, right? But when I violate the independence assumption, right? So here I think I'm sampling from Americans, but I'm getting some of these Duke students in here, right, that are pushing the average up. And it's when you have more than 10% that we actually have a difference between the estimate as if there were independence and that violation. So as we get closer, and so when we get all the way to 50%, where half the sample is Duke and half is Americans, right? The estimated average now is in between the American and Dukes. So we're kind of totally missing the true estimate, right? So that's kind of why that independence between groups is so critically important, because otherwise, if there's actually a difference, it could be masked. And in one of the groups, whatever the superset group is, their estimate is going to be wrong and could be quite wrong if there is indeed a difference. Does this make a little bit sense? Get hopefully a little bit of a visualization as to why you should care about that independence between groups? I hope so. Throw questions in the chat if you don't. But a couple of things, it might be worth, looking at this a little bit. The source code on the slide deck, it will be on GitHub by morning if you want to look at. I didn't include the for loop to actually generate this plot, but this kind of thing I do all the time where I can't quite understand, so I just make my own data set and try to look at it. And so it took me a bit to get this, so it's okay if you need to stare at it a little bit longer. But it to me, it was pretty striking when I got there. I was like, wow, why that 10% rule? Well, it's about 10% that we start to see meaningful divergence between our estimate and what we would have. When it's small enough, we can kind of ignore it. And we'll see this again next week, because there's another rule, right? About 10% of the population. You don't want to have your sample be larger than 10%. And there's another issue when we have quantitative data. Questions? Throw the link in the chat for you. So chi-squared, goodness of fit. Gonna, trying to understand whether or not what we observe is different than what would be expected. And this will show up in all sorts of interesting ways. If you take like 622 or 624, sort of the machine or predictive modeling and unsupervised learning courses, you'll see chi-squareds as, fit statistics for models that you run. Any questions? If not, we can.
Yeah, I have a question. So
yeah, sure.
I know the formula is like very similar to one that I remember. That's called the Z-score. Is that?
Well, the Z-score does this. Is a standard score, so that's going to work for that. That's sort of a rescaling of a metric, so that you have a mean of 0 and a standard deviation of 1. So that works for quantitative data. That won't work for proportions like this.
Right. Okay.
And we'll see Z-scores again when we get to linear regression. But does that help?
Yeah. Like you'd use chi-squared for qualitative or categorical.
Yeah, it's like a categorical data. Yeah. Yep. Other questions? So by way of example, so we're working on our efficacy study of DAX, right? So one of our, so we did a randomized control trial, and one of our outcomes is like success in term 1, right? Which is true or false. And so we have a contingency table where we have the counts for those assigned to treatment, assigned to control. Then we have, it's like a 2x2 table. Then we have, students that were successful and students that weren't successful, right? And so we use a chi-square to see if there's a difference between the treatment and control groups. So, so it's used a lot when you have dichotomized outcomes, true false outcomes. And it could also use, as we'll see very much towards the end of the semester, logistic regression is a way of getting there. But chi-squared is pretty robust.
Yeah, so I guess that's kind of follow along the second part of the question almost, where it's how do you pick which one to use? Is there like a clear cut answer for, this is a particular scenario, so I should use this, or is it kind of wishy-washy? Depends.
There are some pretty strong guidelines, and Angela, maybe you can, I have, I think it's in the slide deck towards, it might even be in my wrap-up slide deck. I know I have this figure I found that that I've tweaked a little bit on selecting which distribution to use, right? It is kind of similar. So there are some good guidelines. So if you're doing, we're still kind of in this null hypothesis testing section. And so if you have quantitative variable and you have large sample size, you can use a normal distribution. In actuality, you're going to use t-test that we'll talk about next week. But even if the sample size is large, people still use the t-test. I don't know. I actually looked to see historically how that happened, but I don't know why the t-test became the standard. It's just became that way. But like, so for this kind of count, proportional data, you're going to just use a chi-squared. There are regression counterparts to a lot of this thing. So it's kind of hard to get into a 1 semester course. I really didn't actually see the big picture until I've had like 4 graduate levels of statistics. But I think so if we think about, see if I can get this right. So there's something called canonical correlation. Well, let me see. Let me explain it this way. Wait, there was another. Okay, let me do it this way. So canonical correlation, right, is sort of a way you can model any kind of data. And then we have something underneath it, which is like called structural equation modeling, which is really just a special case of that. And then help me here, Angela, because it's late and my brain is starting to fart here. So then we have multivariate regression, which is a special case of structural equation modeling. And then underneath that, we have MANOVA, which is a special case of multivariate. Then you get to multiple regression, which is a special case of that. And then you have ANOVA, which is a special case of that, which is this, right. So we'll actually talk about ANOVA next week, and then linear regression, I think, the week after. So this is a big debate, right? So ANOVA is just a special case of regression. So you can get to the same answer through a regression model that you would from ANOVA. So it's just, we're fixing some pieces into particular groups, right? And so you get to ANOVA, and then you have bivariate regression, and then correlation, and down to, sort of simple null hypothesis. So all of these things are kind of nested within more complicated ways to do it. Okay, so the analogy, I think I got this right. So if you think about we kind of teach statistics backwards, right? It'd be almost better to start at the other end. But it's the same reason why in high school we teach physics as a senior level class. And I don't know if you ever noticed, but you get to college, physics is typically a freshman level class. The reason we teach science backwards in high school is that in order to do physics, you kind of need to know a little bit about calculus. And so the mathematics to do physics is hard. And so it takes 4 years to build up the math experience, but right? So if you have physics, right? Well, actually so you have physics, which is kind of the smallest level. And then from there, we expand it to chemistry, and then we can expand it to biology, and then to life sciences, and then maybe to, astronomy, right? Which is sort of the bigger picture. So statistics is kind of structured in a similar way where, if I could teach canonical correlation, but the mathematics to do that is so complicated, and then we could, get down to the special cases, that would be great. But in order to do that, we need to do some pretty fancy linear algebra stuff, and it's just not worth the effort. That was a pretty long digression. And but just structurally to think about this, like these things are all kind of related to one another. And I'll have some pictures. So to answer your question, at the end, after we know the little bits and pieces, there are some sort of decision trees to help you figure out which one to use given your, what kind of data you have.
Right.
So
Okay.
that's why it's important to really know your variables. Are your variables categorical? Are they numerical? Or are they ordinal? Because depending on your answers to those questions, is one continuous and the other one categorical, depending on the answers to those questions and your research questions, the choices, the decision as to what statistical analysis you will use will differ. So that's why it's important to really identify and know what you are working with.
And this is another opportunity for me to reinforce the importance of good descriptive statistics and good data visualization. As a data scientist, I think one of the strongest skills you can bring to a team is being able to understand the data as close to the data as possible. So if you can draw raw points, of course, you have big data, you need to do some kind of summary, but knowing your data is critically important before you start modeling. And quite frankly, you don't often need null hypothesis tests. We sort of emphasize them in academia, or, when we publish, we want to say, is there statistical significance? But, going back to that slide I had a few weeks ago, statistical versus practical, to decide whether or not it's practical, you want to look at your data. So, we have a data visualization course, would recommend, but look at, in particular, I would suggest reading, Tukey and Edward Tufte. Both have written a lot about, so not Tukey. It is Tukey. He has an exploratory data analysis. I think the book is called Exploratory Data Analysis, published in the 60s and is still very relevant. Am I saying that? It's EDA? I can't see it. And then Edward Tufte also just really emphasizes the visualizations over statistical models, and you can learn quite a lot there.
Okay, because I guess one thing that I was thinking about when Angela was saying about really knowing your variables is that you also have some flexibility, right? Because you could, in some ways, change quantitative variables to categorical by like bucketing them, or for example.
Yeah, the one that it just is one of my areas that I've done a lot of work in is Likert response data.
Right.
And so very, very frequently, in fact, I would say the vast majority of researchers just treat Likert response data as a quantitative variable. However, it's not, it's ordinal, because I argue pretty strongly that the intervals are not equal, right? If you think about a simple agreement scale, right? Pretty common, you take a survey, you have strongly disagree, neutral, agree, strongly agree, right? Simple five anchors. I just use myself as an example, but I think this generalizes, and I think there's some research that shows that this generalizes. If we have a single item, think about how much evidence, whatever the question might be, how much evidence does it take for you to go from neutral to agree versus agree to strongly agree? Or you can go in the negative direction, right? So for most people, be like, oh yeah, I kind of agree with that. but I really need to be sure, very, very sure to say strongly agree. So that interval from the midpoint to agree is smaller, if you will, if you think about it in terms of evidence, than going from that second to the highest level, right? And because the intervals are not equal, and then to treat that as a quantitative variable. So if you just convert it to numeric and put it into a model, it thinks going the difference between neutral to agree is the same as agree to strongly agree. And that's a pretty bad assumption to violate, right? You can get around that. And so the way we tend to get around that is we talk about domain scores, which are the sum of multiple items, right? And so that sort of adds some stability to that, because we're summing it across a whole bunch, we can somewhat balance out the sort of within respondent variability in that total score. But it's still not perfect, right? That's still an assumption, and you're still converting data. You're still converting an ordinal variable to a quantitative variable. And by doing that, you just should be aware of what that you're doing it, and that and what the interpretation of your results might be. It could be, I am, and when we get to regression, we talk about coefficients. I am extremely careful to interpret the magnitude of a lot of these things. I really look at the direction, particularly as we get into multivariate stuff, because the magnitude of some of these estimates that we're going to do are not really comparable, because the distributions of each independent variable is going to be different. So long-winded sort of precursor to some stuff that's coming up. So but I like your question, Santiago.
Thanks.
Anybody
Yeah,
else have
that question gets at a lot of decisions that we as researchers or data scientists have to think about, right? Because if you convert or transform a continuous variable, for example, into a categorical variable, why are you doing that? There are pros and cons for doing it, right? So unless there's good reasons, that's a good question to ask. And then after that, what is the appropriate analysis to run? Because that might change when you change the variable type.
The other one, let's see if I can, please excuse my spelling, but Google will fix it here. So the other way to go about it, so Frank Harrell, he's at Vanderbilt, written a really great regression book. He's on Twitter. I would highly recommend following him. Super smart guy. And he frequently goes off on research, because the other way, so we talked about taking like an ordinal and making quantitative, but a lot of times what people do is take a quantitative variable and dichotomize it. Yep. And that's like, he's all over that. And I sort of largely agree with him. There are some very specific examples where it's useful. But you're leaving a whole lot of information and variance on the table when you do that. A lot of information. So it goes both ways: quantitative to qualitative, qualitative to quantitative. And oh, here we go. Here's oh wait. Oh, this is okay. So somebody's linking data. So I'll throw this link in the chat if you're so interested in that. But at a minimum, look him up on Twitter and follow him, because he points to all sorts of interesting papers and has very interesting insights. And when we talk about regression, so save that question. You can ask it again when we get into the regression context, and we can kind of show, maybe we can come up with some examples where things can go very badly very quickly. All right, well, 9:31. It's late here in New York, so we can call it a night. Unless there are other questions, I'm happy to stay on, but otherwise you can ask in Slack. And I think I responded to everybody's question. If you sent me a question in the last 2 days, and I didn't respond, you can send it to me again in the morning and I'll get to it. Just make it bubble to my inbox. All right. Have a good night, everyone.
Thanks, you too.